welcome back to Engineering Nature. This is the extension video where we are talking about the wastewater treatment by mean of hydrodynamic cavitation. And in the first part I had create a geometry of cavitator reactor and just we have mashed it. So now in the second part we will discuss about the solution setup and case setup file. Now once you open the fluid, it will shows you the mesh quality which we are talking about. This is what mesh we are using with inlet as well as outlet sections in this geometry. Now you go to the general settings where we can scale up or scale down the geometry. You can change the unit in which you want to see the geometry. You kindly check the mesh, and in the display sections you can enable the display of various geometry. Now here we are considering the transient simulation, so you just select the transient one. Now in the model sections, let me show you the multiphase models available with us. We are selecting or we are using volume of fluid as well as mixture model for this particular case. In the volume of fluid, it's automatically convert this simulation into the transient mode, and with the mixture model, yes, you can see the dispersed phase. With the help of volume of fluid, you can see the sharp interface. Now for simplicity, you can go with a mixture model. For clear interface tracking, you should go with sharp interface. Now once you define the multiphase model, this tab is automatically open, but before that you have to define the material. Go to the material sections and you have to add the material that is the water. In our case, we have to choose water liquid. These are the property for water liquid. You just copy and close that, so it will add in this library, material library. We also required the vapor phase of that water, so you have to choose that vapor phase. These are the property for vapor phase. You simply copy that. So once you copy this material, and now it's reflected into the model section, so you go to the model and then you can define the primary as well as secondary material. So now my liquid water liquid is the primary phase for this particular problem, so you just select that and just give the name for that, so it will accordingly, that property is taken care by solutions. And secondary phase I am considering as a water vapor. Once you define the primary and secondary phase for your problem, you just go to the phase interaction setup. Now in the phase interactions, you can define the surface tension constant. For the water, I am considering that surface tension constant of 0.072. Now you have to define the mechanism, right? Phase interaction, you just go to the heat and mass transfer reaction and activate the cavitation mechanism. In the cavitation mechanism, we have two model, SS as well as ZZB. So you can select any one, but ZZB is more accurate. There you have to define the vapor pressure of the volume of the water. Once you define the cavitation model, you just go to the turbulence model. In current case, I am considering K omega with SST configurations, that will more precise, which will taken care the boundary. Once you define the turbulence model, you go to the boundary conditions. Let me define the inlet as well as outlet boundary condition. At the inlet sections, we are actually supplied the high pressure water, that is of 5 bar of water pressure, and in the second case I will consider 10 bar of water pressure. So at the inlet, you just specify the pressure inlet. I am considering 5 bar, and in the supersonic gauge pressure, you just consider the near about the 5 bar of pressure. You have to specify the intensity and hydraulic diameter for this inlet sections. So hydraulic diameter accordingly you just specify. Now at the pressure outlet conditions, we have atmospheric outlet, so you have to supply 0 gauge pressure, so it will take care for outlet sections. You should define the specification for intensity and hydraulic diameter. Now in the wall, you have to select boundary type as a wall. Now in the inlet section, see at the inlet we are supplying the water, so your the vapor fraction should be supplied as a 0. That means entire inlet is filled with water. Now in the solution part, you just use the coupled scheme for pressure velocity coupling. You just select green gauge cell based method, and for momentum we will consider first order upwind scheme initially, then we switch over to the second order upwind scheme. Now you just go to the monitor where we can define the residual that will decide the accuracy of iterations. So I will consider the residual of 10 to minus 5 for all equations during the iteration. So then after, you can initialize the problem. You can do the standard initialization from inlet, or you can also do the hybrid initialization. Since we have the inlet condition is available with us, so I will just initialize standard initialization from the inlet. Once you initialize the problem, you can see the calculation activity window, where I can set the animations for my simulation. During the simulation, I want to see the liquid fraction of or vapor fraction, not liquid fraction, but vapor fraction of the water. So you just select that contours for as an animation frame, right? So this is what water vapor fraction what I want to see. Initially there is no vapor, so it's entirely blue color indicating the entirely filled with water, so the vapor fraction is 0 for that. So here ultimately at the throat section, I want to animate that vapor fraction. So you just use that active window that will give you the animation for this particular the screen. Then you can start your calculations. Since it is a transient solution, so you have to define the time step size. So you should keep this time step size in the range of 10 to minus 7 second. For each time step size, I am considering 20 iterations, so it will give the better conversion. Otherwise you will have the diversion due to the exceed of coherent number. So see, it took lot of time to solve entire problem. So in between I stop that iteration and I just check the vapor fraction which I can get at the throat section. Now to accelerate the formation of bubble, what I will do, I will just increase the inlet pressure. So in intermediately I just stop the iteration, and then what I will do, I will simply go to the boundary condition and change the inlet pressure from 5 bar to 10 bar of inlet pressure. You should also change accordingly that initial gauge pressure and just apply that. So I just use 10 bar of inlet pressure, and then again I will start the solution. So again I will initialize. I just do the hybrid initialization this time, and after hybrid initialization you just start the calculation activity. So due to it's a multi-phase problem, it took a lot of time to complete the solutions. So let me show after a certain period of time what should be the vapor fraction will form near to the throat section. So this is how vapor formation can appear on that throat section, and it is continuously, as time proceeds, it is continuously elongated and moving towards the downstream. That is what expected. Like this throat is used to generate the larger amount of cavitation zone or the cavitation intensity. Let me, after 5000 iteration, let me stop this and show you the result for the solutions. I just write this case and data file before show you the result. Go to the contour sections, and in that contour sections you can go just visualize the velocity contours. So we have almost maximum velocity at that after throat sections we have maximum velocity which is visible, almost 46 meter per second. You can also see the pressure. We have pressure variations. Initially we have high pressure almost 10 bar, then suddenly after throat it will decreasing in this way. So you can also see the turbulent kinetic energy. Obviously, due to the formation of vapor, there is an interface where we have maximum turbulent intensity. Now let me check the velocity vector. So that vector will give you the idea about the flow path behavior. See here, we have huge recirculations. Let me change the scale and skip for better visualization. So here, see, in this zone we have a huge recirculation which will leads towards the cavitation formations. You can check the animations, almost 500 frames I have after 5000 iterations. So with the help of that 500 frames, you can actually create the animation sequence. You have to go to the right sections and you just write the video files. So once you write that, obviously you have video files which is which took a lot of time, but yes, it's give you nice video animations. So with this video we can clearly see the propagation of cavitation bubble which will elongated in the downstream, and we can feel how the phenomena will work through this type of geometry. So this is how you can analyze the problem for such kind of case. So that's it for today. Thank you very much. You can stay connected with this channel. Subscribe Engineering Nature and press bell icon for more interesting video related to the ANSYS Fluent. So goodbye, take care.